All right, now we're going to get started. If you don't have your notebook out yet, make sure you're getting that out. It's going to be important you follow along today and kind of this whole chapter by taking some notes. If it's important, I'll make sure you get written down. Try to title an empty page. Just all you really need to write down is 7.1, and then the inverse trig functions. Everything I underline. That's what I'd write. That's what I would title this. You don't need all those words. Good job on your test yesterday. I think you guys had the highest average of our three, so
That's right.
good job with that. All right, so we're going to get started. Looking at the problem on the left side of the board, those first four functions, those first four graphs are all functions. Those bottom four graphs are not functions. Take a second and try to tell someone one reason you can think of why the top ones are functions and the bottom ones aren't functions. The what test?
Horizontal line test.
Horizontal. Vertical? Vertical or horizontal? Oh. Gia, you're skipping ahead. We'll get to that. You said too much. What were you thinking over here? Yep, so the reason why these top ones are functions, this should have been Algebra 1, maybe 8th grade math. They're all functions because they all pass the vertical line test. So if you said vertical line test, you were right on the money. Remember, the vertical line test means that there has to be one output for every input. There's going to be one y for every x. That's what our vertical line test is testing. The ones on the bottom, we try to do the vertical line. Let's say the vertical line of x is 1, crosses the function twice. That means we have two outputs or two y's for our one input. So it fails our vertical line test. The second function, 1, 2, 3. I don't know if that was quite vertical, but it would fail it 3 times. That third graph, it's a vertical line, so just has to fail the vertical line test once. If you overlaid it there, it would fail it infinitely many times because you can only touch it once. And then that fourth graph, you can see fails our vertical line test as well. So remember, the definition of a function is every output is going to have one input. And the way we can test that on a graph is with our vertical line test. So now number 2, write down in your notebooks y equals x squared. And once you get that written down, I want you to find the inverse. This was probably a couple years back, so let's see if you guys can remember. What do you think you do for the inverse? Do you remember?
All I can think about is the negative 1. Yeah, that's what I think.
Well, that's how we set it out. That's like how we show. So that's good. That's definitely fine. The biggest thing with inverses is just your input and output swap. So you would swap your x and y, and then solve for your y. You get anything for our inverse or no?
I got the inverse.
What's the inverse?
Y equals x squared.
Y equals x squared?
Do I have to write the graphs down too?
Well, no, that was our function. I wanted you to find the inverse of y equals x squared.
Don't we have to do like the x thing? Like try to get the x onto one. What was the y on this?
Swap your x and y, solve for y.
Okay, I know what I'm doing now. Okay, I know what I'm doing.
Were you guys able to figure out the inverse or no?
Nah.
I've been talking about with other people, inverse, we just swap our x and our y and we solve for y. Do you remember that? Is
I
that
do
right?
recall.
Okay.
All right. It comes off.
All right, so when we're solving a function for its inverse, the first thing we're going to do is we're going to rewrite it. But x and y are going to swap places. So instead of y equals x squared, we would write x equals y squared. From there, any equation, remember x is always our input, y is always our output. Any equation, you have to have the output by itself. So we have to solve this equation to get y by itself. What can we do to both sides to get rid of that exponent? Yep, square root. So then our final answer would be the square root of x equals y. Remember, the square root is positive and negative. That would be the inverse for y equals x squared. Remember, in general, what an inverse is going to do is an inverse function takes your original function rule and it flips which one's the input, which one's the output. And that's what we showed algebraically, but also kind of graphically. We'll see on the next slide what that means. So moving on, is y equals the positive and negative square roots of x a function? What do you guys think? Maybe? That's its graph right there. The picture on the left. No? Why not, Chris? Doesn't pass the vertical line test. It has multiple outputs for every input. So this is what we just found out from that example. Just because a relationship is a function doesn't mean its inverse is going to be a function. Remember, the square root of x, we just found out, was the inverse of x squared. X squared, past the vertical line test, was a function. Square root of x, not so much, doesn't pass our vertical line test. So once again, it's the same 8 pictures on the right-hand side, but we're only going to look at the top row. We'll call it 1, 2, 3, and 4. I want you to take about a minute. You can talk to someone, but write down in your notebook, which of those 4 do you think would still be a function if we inverted them? Like if we took those graphs and whatever their function rule was and found its inverse and then graphed that, which one do we think would still be a function? 4?
Wait, would still be 1.
What you think of Tia? 2? Any of the other ones? What function is this? What function is number 1? Yeah, it's a parabola. It's also it's x squared. So we know x squared's inverse. We just saw x squared's inverse is not a function, so it can't be number 1. Remember, an inverse is, to get an inverse, we swap places of x and y. One way to kind of see that graphically, to see x squared and then its inverse, if I want to see if it's inverse, like what its inverse is going to look like, you kind of just look at it sideways. It's kind of a funny visualization, but the x-axis and the y-axis switch. That's essentially how we get our inverses graphically. So kind of thinking about that, raise your hand if you think number 2 would still be a function if we inverted it. Okay, it's about half. Yeah, I agree. Number 2 would be a function if we inverted it. What about number 3? Chris? You're trying to be bold? Didn't work out for you. Number 3. I appreciate taking a chance, but not this time. Okay, so number 4, what do we think? Anyone? All right, number 4 is not going to be a function either. Sorry, Alexis. So number 2. What do we notice about number 2? How do you think we could tell from the graph that number 2 out of all of those would still be a function if we inverted it? Straight line? Yeah, straight line, that's one. Lines, straight lines, as long as they aren't exactly vertical, or exactly horizontal. As long as they have some slope, we can invert it. So that's a great point. Anything else? Because there's functions that are invertible that are not straight lines. So how do you think we could tell from a graph that something that its inverse is going to be a function? Any ideas? Yeah, horizontal line test. Gia was keeping her mouth shut because she was saying that kind of early. I didn't want her to spoil it. The way we can tell from a graph if its inverse is going to be a function is the horizontal line test. It works exactly the same.
No, I said at the beginning.
Did you guys back up? Thank you. The horizontal line test is how we can tell from a graph if its inverse is going to be a function. Number 1 fails the horizontal line test. Number 3 fails the horizontal line test. Number 4 fails the horizontal line test. Funny enough, looking at that bottom row, even though that one wouldn't have been a function, its inverse would have. Same with this one. Both of those would have been, their inverses would have been function, but their inverses would have been functions, but the functions itself were not functions. Mouthful. So the point of all of this was to establish what we call one-to-one. When a function is one-to-one, that means it is exactly one input for every output and one output for every input. Another way to think about that is every one-to-one is a function, whether it's just kind of in its base form or if it's in its inverse. And that's going to be really important as we look at our inverse trig functions. The way we can tell graphically if something's one-to-one, I'm going to need you guys to write this down, is an equation, a relationship is one-to-one if it passes both the vertical and horizontal line test. Once you get that written down, I need you to write down these two lines as well. One-to-one, the way we define it in this class, is every input has exactly one output, and every output has exactly one input. We're going to take our trig functions and we're going to need to fix them up a little bit, but we want those functions to still be functions when we're working with the inverse trig. And the way we're going to do that is going to rely on making them one-to-one. Any questions with one-to-one? Remember, from a graph, the way you can justify that a relationship is one-to-one is if something passes the vertical and horizontal line test. The way we say it, just kind of in math speak, is every input has one output, every output has one input.
Stop looking at me. You got glasses, excuse me.
So now, what's this function? Parent sine function. So the nice thing about these inverse trig functions is the way we were kind of graphing them with amplitude and period and all these shifts, we don't really have to worry about that for the time being. These inverse trig functions are just going to be completely off of the parent functions. So looking at sine of x.
Wait a minute, can you say what you just said again? I lost it.
Okay. Thanks for letting me know. Right now, we spent like the last week or two worrying about what happens if we shift these parent functions left or right, stretch them vertically or horizontally with a period change or an amplitude. We don't have to worry about that right now. Right now, we're just worried about the parent functions. So looking at the parent function of sine, and I don't really like how the x-axis are in here. Everywhere you see p, it means pi. So p over 2 is pi over 2. Negative p over 2 is negative pi over 2. That blue segment, the one that I kind of drew over, that's going to be the domain or the inputs that we restrict our parent sine function to. And the reason we do that is in order to find values with an inverse sign, we need our sign to pass the horizontal and vertical line test. We need to find a piece of sign that's going to be 1-to-1. When we're looking for that piece, the first thing we're always going to do is we're always going to include from 0 to pi over 2. What quadrant on our unit circle? It goes from 0 to pi over 2. Quadrant 1, yep. What about from pi over 2 to pi? 2. And then it would keep going, right? 3, 4. But what about if we go in this direction? Which quadrant goes from 0 to negative pi over 2? 4, yep. Good. And then negative pi to negative pi over 2 would be quadrant 3. When we're looking to restrict our trig functions to make inverse trig functions, we're looking for 2 quadrants. We're always going to include 0 to pi over 2 or quadrant 1. We really like quadrant 1 because every single trig function in quadrant 1 is going to be positive. So we don't have to worry about playing with the negatives. From there, we're going to look at quadrant 2 or quadrant 4 to see which one allows our function to be 1-to-1. Looking at quadrant 2, if we restricted this to just 1 and 2, we would fail our horizontal line test and it wouldn't work. So that's why for sine, we restrict our domain to quadrant 1 and quadrant 4. So I need you to write that down. Inverse sine, and the way we show that is sine to the negative first exponent, is going to be quadrant 1 and quadrant 4. It's also important that we know the x values that go along with that. So we're going to use square brackets and say that our inverse sine can go from negative pi over 2 to pi over 2. So I need you to write down both of those lines in your notes. That's going to be very important. We call that our inverse sine domain restriction. Negative pi over 2 to pi over 2. What that means for us when we're using our unit circle is when we're computing inverse sine, we only look at quadrants 1 and 4. Whatever you need to do, whether it's cover up the left-hand side of your unit circle with your hand or cover it up with a piece of paper, only look at the right side of the unit circle when we're trying to compute an inverse sine. From there, and it'll make more sense once we start going over the examples. Remember, an inverse function switches your input and your output. So far, for all of chapter 6, we would be like, what is sine of pi over 6? Our input would be pi over 6. And then what would our output be? What would you say? Yep, 1 over 2. We knew that the output for sine was our y-coordinate. And we knew we just had to look at our input, and our input was our angle. Whatever the y-coordinate was at our angle was going to give us our sine value. Now, our input and output are going to be flipped. So when we have an inverse sine, the number that's going to be inside that parentheses is going to be a y-coordinate. For example, we might ask you, what is inverse sine of 0? An inverse sine of 0, we would have to see on this half of the unit circle, where do we have 0 for a y-coordinate? We see it's right there. So then our answer, we give in radians, here would just be 0. We are swapping our inputs and our outputs. The one thing that we need to be aware of is we said our answers for sine could only be between negative pi over 2 and pi over 2. If I asked you the sine of the inverse sine of negative 1/2, the inverse sine of negative 1/2, what would you say? First, you have to look at, okay, where on quadrants 1 and 4, where's my y coordinate, negative 1/2? Okay, it's right there. Oh, my answer is 11 pi over 6. You would receive partial credit for that, but you don't receive full credit. And the reason is 11 pi over 6 is not between negative pi over 2 and pi over 2. So when we're working with these inverse trig functions, the way we need to think about these radians is not as 11 pi over 6, but it's as negative pi over 6. We don't think of this as 7 pi over 4. We think of it as negative pi over 4. We don't think about this as 5 pi over 3. What do you think we think of it, Chris?
Negative pi.
Negative pi over 3. And then that right there is going to be our negative pi over 2. We have to make sure our answers are inside that restricted domain that we figured out. So now we're going to look at some examples. Examples of inverse sine. This first one, inverse sine of 1. Whenever I have an inverse question, the first thing I'm going to do is say, okay, what's my base trig function? Here it's sine. All right, sine's the y coordinate. From there, okay, it's inverse sine. Inverse sine, I have to look at quadrant 1 and quadrant 4. So I'm writing it out now. You could just think that. So then I take out my unit circle. I cover up quadrants 2 and 3, and I only look at quadrants 1 and 4. Inverse sine, what's inside the parentheses, is going to be the y coordinate we're looking for. Here we see that y coordinate is 1. So we have to look and see where do we have the y coordinate of 1. Here we see that the y coordinate of 1 happens up there. And so our answer is just going to be that radian value. All of our answers are always going to be in radians. So if you're not super comfortable with the radians, maybe take some more time to go back over your unit circle. You got to be really strong with radians in this chapter. So our answer would just be pi over 2. The next one, inverse sine of 1/2. Okay, sine's going to be the y coordinate. So I need to figure out the y coordinate that's 1/2 and quadrants 1 or 4. As I go down, that's 1, that's 3 pi over 2, root 3 over 2, root 2 over 2, 1/2. There we go. So then I found that that's my point. I just have to identify the corresponding radian, corresponding angle measure. Here, it's pi over 6. So that's my answer. Question? Nope. Because it's in quadrant 1. If your answer's in quadrant 4, that's when you have to worry about the radian being negative. Here we were just looking for where's our y coordinate, positive 1/2. And in quadrants 1 and 4, that only happens at pi over 6. Great question. Now inverse sine of root 3 over 2. I just got to figure out quadrants 1 and 4. Where's the y coordinate, root 3 over 2? That's going to happen right here at pi over 3. I now want you to attempt those bottom 3 by yourself. You might want to pull out your unit circle. I know the one on this board's a little bit small. Great, I'm glad you guys asked that. Arc sine is another way we write sine to the negative first power. It means the same exact thing. Yep, arc sine is inverse sine. In this class, what? Everything's on the test, Chris. Come on now. A lot of colleges, I know some of my classes at Butler, the professors would only use arc when they were talking about the inverse trig. Mostly in this class, we're going to use the -1 as the exponent, but you have to be able to at least identify both. So arc sine of 1, what's that answer going to be? Pi over 2. How'd you know that? Yeah, these are the same exact questions. Arc. Question?
R. Just for, yeah, just to make sure. So like the fourth quadrant, it's kind of just like a negative first quadrant in a way.
Correct. 100%. 100%. So Gia just said something really smart I want to share with everyone. That fourth quadrant, one way we can think about that is it's just our negative first quadrant. So if you're looking, and I think this is what she meant, okay, if it was like arc sine of negative root 3 over 2, well, you could just figure out where sine is positive root 3 over 2. Oh, it's at pi over 3, and then just make it negative. That could be one kind of workaround if you don't like counting backwards in radians. So what do we get for this one? Anybody want to share? 4 pi over 3?
No.
What'd you say, Alexis? Yep, so that,
Because it's right here, right? Because you said, so, oh, wait.
what quadrants do we look at? Great. What quadrants do we look at for sine, inverse sine? 1 and 4.
That's wrong. Oh, yes.
So looking at quadrants 1 and 4, our y coordinate is going to be negative 1 over 2 at 11 pi over 6. Remember, we can't put 11 pi over 6 as our answer. We need to make that between negative pi over 2 and positive pi over 2. So we can start at 0. We go negative by pi over 6. So that's going to be our answer. Negative pi over 6. What do we get for inverse sine of root 2 over 2? Question? Thanks for asking. Yep. So first thing I'm thinking, inverse sine, I'm looking at quadrants 1 and 4. Sine is going to be the y coordinate. And I'm looking at, I need to find in quadrants 1 or 4. One's my y coordinate going to be negative 1/2. I find by looking at my unit circle that the y coordinate is going to be negative 1/2. Right there. So the answer is we need to figure out the angle measure. But the angle measure we're using isn't going to be that. Our angle measure is going to work in the negative direction to just be that. So what I was saying when I went from 0 to magically negative pi over 6 is I had to go in the opposite direction. I had to go clockwise. And I went clockwise by pi over 6. When I go clockwise or I go in the negative direction, instead of pi over 6, it's going to be negative pi over 6. Another way to think about it is whenever you're in quadrant 4 and you're trying to figure out your radian, it can be whichever radian you see, 2 pi minus whatever radian you see. Here the radian you saw was 11 pi over 6. Sorry, I have that flipped. It would be the radian you see minus 2 pi. Essentially, we need to find the coterminal angle that's between negative pi over 2 and positive pi over 2. The coterminal angle, the way we would find that negative coterminal angle is subtract by 2 pi from our radian. When we're adding or subtracting fractions, we need a common denominator. To find that common denominator, it would be 2 pi, so negative 2 times 6, that gives me negative 12. So there would be 11 pi over 6 minus 12 pi over 6, and that's where I get negative pi over 6. So it's really whatever works for you. If you need to go through and find the negative coterminal angle, that's fine. If you want to start kind of, you don't have to relearn the whole unit circle, but relearn these 4 values as negative pi over 6, negative pi over 4, negative pi over 3 and negative pi over 2. That works. Really, for this chapter, we're going to be using quadrant 1, 2, and 4. And quadrant 4 is the only time we're going to be messing with the radians. Cool. Great questions. I really appreciate it. Any other questions with inverse of sine? Great. So now we're going to look at cosine. Cosine plays a little bit nicer. What quadrants is that blue section going to be in? What? 2 and 3. So that blue section starts at 0 and goes to pi. Yep, so that's going to be quadrants 1 and 2. On your unit circle, the quadrants that are between 0 and pi are quadrant 1 and quadrant 2. So that's going to be our restriction for inverse cosine. You need to make sure you have this written down. Inverse cosine is going to be quadrant 1 and quadrant 2. Our domain restriction for cosine is going to come from these two values. So our possible answers for inverse cosine are going to be the hard brackets 0 to pi. The way we figured out that it was going to be these two quadrants is, remember, when we're figuring out our one-to-one domain restriction, the first thing we do is we're going to always include quadrant 1, or from 0 to pi over 2. From there, we can either go back a quadrant or forward a quadrant. If we went back a quadrant, we would have failed our horizontal line test. And so our inverse cosine would have given us duplicates. It would have been really messy. We don't want that. So instead, for cosine, we went forward. Because if we go forward, no matter where we try, we're going to pass our horizontal line test. And we're going to have a one-to-one function that's invertible and still gives us a function. So now we have our domain restriction for cosine. We're going to kind of go right into the examples. I want you to try these examples by yourself. Before you kind of hop into them, is cosine the x or the y? So this time, there's two differences between inverse cosine and inverse sine. Inverse cosine, we're looking at quadrants 1 and quadrant cosine. Yep, cosine is 1 and 2. Sine is 1 and 4. The other difference is we're looking at the x coordinates for cosine. We would be looking at the y coordinates for sine. So take a second and attempt these 4 questions. Yes, your answers are going to be the radians. That second domain restriction I had you guys write down, from 0 to pi, those are the range or your possible answers for the inverse. Use your own unit circle if you're having trouble seeing the screen. Oh, the problems? What do we get for inverse cosine of -1? Pi? Yep. We're looking for in quadrants 1 and 2 so we can cover up the bottom half where our x coordinate is -1. That's going to happen right at pi. So what about arc cosine of -1? Pi, yep. Remember, arc cosine and cosine of -1, that both means just inverse cosine for us. That means the same exact thing. What about inverse cosine of 0? Pi over 2, yep. We're looking for, in the top half of our unit circle, where's our x coordinate 0? That happens right there. Right at the top. So our radian is going to be pi over 2. Last but not least, we're looking for inverse cosine of negative root 2 over 2. 3 pi, oh, I'm so sorry. 3 pi over 4. Yep, I agree. Our x coordinate right there, as we can see, matches up with the one we were looking for. 3 pi over 4. With cosine or any of the other trig functions that we restrict to the top two quadrants, quadrants 1 and 2, you won't have to worry about switching the radians. Our domain restriction already matches the radians that we have. 0 to pi. Yep.
So only the fourth quadrant we have to worry about.
Yes. Yep. And one way that I think could really help you think about it is that fourth quadrant for the radians is just going to be the negative first quadrant. So it just reflects right across. Almost. Any questions about inverse cosine? Great. So first things first, and then we're going to kind of preview inverse tangent a little bit. The homework for this section, this chapter is going to be out of the textbook. Those homework exercises are listed on Canvas. Just click on the chapter 7 button, go down beneath the calendar, you'll be able to see all those homework exercises. Homework 6 is due Friday, so once again, you got to turn it in, have it in by Monday to get full credit. I think if you want to get started on it tonight, you'll be able to get through most of the exercises. If you see something unfamiliar, that just means we're going to cover it tomorrow, so don't stress out about it. But definitely, if you're someone who wants to stay on top of things, don't want to save homework on the weekend for yourself, you can get a head start on homework 6 tonight.
This is gonna be 2 and 3. Quadrant 2.
All right, so if I could get the eyes back on me, tangent is a rule breaker, right? And it's going to be really important that you guys understand how we get the domain restrictions for inverse tangent and then how we're going to use them. So tangent, we know this is our parent function of tangent. We know tangent's going to squiggle up, or it's going to have those vertical asymptotes. Remember, when we were graphing tangent, our horizontal shift, we would start at pi over 2. This is just, once again, we would start there because that's where our asymptote was without a shift. So getting back to restricting the domain of tangent, which quadrant do we know we're going to include? Quadrant 1, yep. Our quadrants are always going to include quadrant 1 because everything's positive. Why wouldn't we include it? So we know we're going to include from 0 to pi over 2. Now here, if we're just looking for our vertical and horizontal line test, please make sure you're looking at the board. I don't want you to miss this. If we went forward a period, or if we went forward a quadrant or backwards a quadrant, we would pass our horizontal line test. Agree? There's going to be nowhere in this section or that section that messes up our horizontal line test. But there's actually one more component of being one-to-one that we include when we're looking to restrict our inverse trig, and we want our domain or our x values to be continuous. Now there can be a vertical asymptote on the boundaries, but we don't want a vertical asymptote right in the middle of the two quadrants we're looking at. So we're looking at quadrant 1. Do you think we're going to go for tangent back to quadrant 4 or forward to quadrant 2? Yep, back to quadrant 4. We want these asymptotes to be kind of our edges for our inverse tangent. If we did 1 and 2, that big nasty asymptote would be right in the middle. It would be right in the middle of our domain, and it would just be ugly. Here, we're going to have our tangent value, our inverse tangent values be continuous. So looking at tangent, once again, write it down, inverse tan. We're going to restrict it quadrant 1 and quadrant 4. Make sure you have that written down. And then our restrictions that include negative pi over 2 and pi over 2 is going to look a little bit different. And this is really somewhere where tangent is a rule breaker. What's our tangent at pi over 2? Anyone remember? Undefined, yep. Remember, it's a straight up and down vertical. 1 over 0, undefined. What's our tangent at negative pi over 2? Undefined. Negative 1 over 0. So we went through all this work to make sure all of our outputs have exactly one input and all our inputs have exactly one output. But here, pi over 2 and negative pi over 2 are both undefined. And that's going to be a problem for us with our inverse tangent. The way we solve that is we use a soft bracket on negative pi over 2 and we use a hard bracket on pi over 2. So that means our possible tangent answers can go up to, but can't touch negative pi over 2, but then can touch pi over 2. It's really just for this question right here. What is the inverse? I'll write it like this. What is our arctan of undefined? That is something that you can get asked. It looks weird, but that could be a question. If we didn't restrict our domain like that, you would have two answers. You would have positive pi over 2 and negative pi over 2. That can't work. Remember, we need one input for one output. But now that we said that negative pi over 2 isn't a possibility, that means that our answer for this question is just going to be pi over 2. Does that make sense?
Yeah.
I think we're going to wrap up here for the day to make sure we stay equal with the other periods. Before you put your stuff away, can you just kind of give me a thumbs up, middle, or down with how you feel about these inverse trig functions on day 1? Okay. Awesome. We're going to look at those tangent examples tomorrow. If you find a tangent problem on your homework, I would just skip it till you come to class tomorrow. There's going to be there's just an easier way to do it than what you might guess.